ideal gas equation, we can do the following. Since PV equals nRT, we can rearrange that to solve for N times R. As I said, in the experiments that we just described, N was the same, so it becomes a constant in the calculation, and R is a constant all the time. So if you keep the number of moles the same, what we can say is that P1 V1 over T1, notice it's PV over T, P1 V1 over T1, which is NR, is equal to P2 V2 over T2, because that's also N times R. In other words, the number of moles of gas after you do the change, let's say you change the pressure or the temperature, will be the same as before you did the change, because you have a closed system and no gas escaped and no gas was pumped in. So with that in mind, we have the relationship when the number of moles is the same. P1 V1 over T1 equals P2 V2 over T2. So how can we use this? Well, let's say we have a sample of gas at what's called standard temperature and pressure, STP. And standard temperature and pressure is defined as 0 degrees centigrade and 1 atmosphere. We find that that gas occupies 2.5 liters under those conditions. And we can ask the question, what if we change the conditions? What if we raise the temperature to 25 degrees C and drop the pressure to 75 kPa, kilopascals? You'll notice that 1 atmosphere is 101 kilopascals, so 75 kilopascals represents a drop. Well, first, let's get a feel for what might happen. As a result of the temperature change, would the volume increase or decrease? Well, Charles found that there was a direct relationship between volume and temperature, and that relationship was linear, and the volume increased with increasing temperature. So in the case of the reaction of the volume to the temperature increase, we would expect the volume to increase. Likewise, we're dropping the pressure. And if we drop the pressure, remember pressure times volume is a constant. If P goes down, V must go up. So we would predict in this case that both of those effects, increasing the temperature and decreasing the pressure, would increase the volume. All right, so let's do the calculation and see what happens. We're solving here for a volume, so we'll call that V2. And according to the equation up here, V2 will be P1 V1 over T1 times T2 over P2. And that's going to be P1, which is 1 atmosphere, V1, which is 2.5 liters, over T1, which is 0 degrees STP, but that's 273 Kelvin. The temperature has to be in Kelvin. Now we're going to multiply that by T2, which is 298 Kelvin, divided by V2. Well, V2 is 75 kPa, but 1 atmosphere is 101 kPa. And if you do that math, it turns out the volume has indeed increased to 3.67 liters. Okay. All right, let's use the ideal gas law to predict directly one of the ideal gas variables. If you know 3 of the ideal gas variables, for example, temperature, volume, and pressure, you can calculate the 4th, which would be the number of moles. But let's take a slightly different problem. Let's calculate the volume of 0.15 moles of a gas that's at 25 degrees and is exerting a pressure of 125 kPa. We have our 3 parameters, moles, temperature, and pressure. Remember, the ideal gas equation is PV equals nRT, so V must be nRT over P. Okay? We need N in moles, 0.15 moles. R is 0.0821 liter atmospheres per mole degree. T, it's 25 degrees C, so that's 298 K. And again, our pressure, which is again in kilopascals, needs to be converted 125 kPa times 1 atmosphere over 101 kPa. And if we do that math, it turns out that the volume of this gas is 2.96 liters. So we can solve the ideal gas equation for any of the variables that you see, and we can calculate that variable as long as we know the three others. Remember, R is not a variable, it is a constant. This represents another way to calculate the number of moles. So we know that if we have the mass of a substance, we can use the molar mass to calculate the number of moles. We know that if we know the volume of a solution with a given molarity, we can calculate the number of moles. And so finally, now we have an ideal gas equation that also allows us to calculate the number of moles. All right, so what we're going to do then is use that to do a stoichiometric calculation. So we might ask, if we have the reaction of sodium with water to form sodium oxide and hydrogen, what volume of hydrogen would be produced by the reaction of 2.35 grams of sodium with excess water at STP? Now the key idea here, as before, is that we have information about one thing, but we're asked for information about something else. So we need a way to relate the sodium to the hydrogen. And we do that with the balanced chemical equation. There are two sodiums that react for every hydrogen that forms. That's the key idea. Okay, so what we'll do is proceed as we always have, starting with what we know, 2.35 grams of sodium. Now we're going to need to convert that to moles if we're going to use the balanced equation to relate the moles of sodium to the moles of hydrogen. And it turns out that the molar mass of sodium is 23.0 grams. So again, from the periodic table, I find the molar mass of sodium. Again, just as before, I can relate the moles of sodium to the moles of hydrogen by saying 1 hydrogen over 2 sodium. And if I do that math, it turns out that I have 0.0511 moles of hydrogen. Now that calculation is identical to the one we did way back in chapter 3. However, now we want to know not the mass of hydrogen, which would normally be what we would do, but rather the volume of hydrogen. And as you just observed, V is going to be nRT over P. Well, we know the moles. It's 0.0511 moles. We know R, it's 0.0821 liter atmospheres per mole degree. We know the temperature. Standard temperature is 273 Kelvin. And we know the pressure, 1 atmosphere. And if we do that math, it turns out we have 1.14 liters of hydrogen. So all we have done is to use exactly the same stoichiometric calculation to determine the number of moles of hydrogen gas, and then instead of using its molar mass to figure out the mass of hydrogen, we use the ideal gas law to figure out the volume of hydrogen under standard conditions.